All right, let's talk SPM chemistry. If you're gearing up for that exam, Group 1 is pretty much guaranteed to make an appearance, right? So in the next few minutes, we're not just going to skim the surface of the alkali metals. Oh no, we are going to dive deep and really get a handle on the patterns and the logic behind them. The goal? To make sure you can tackle any question they throw at you. Ready? Let's do this.
Okay, so understanding all the concepts we're about to cover, that's step one. That's the foundation. But, and this is super important, to really make it stick for your exam, you gotta practice. It's all about active recall. And that's why I wanna quickly show you this awesome tool.
So, right there on your screen, you'll see a QR code. Go ahead and scan it, or just type in MCQ SPM.com. Seriously, it's a goldmine of past year questions. There's also an app for it on the Google Play Store. My advice? Bookmark it. And after we're done here, jump on there and try a few questions. It's the best way to see what's really sunk in. All right, tools in hand, let's get into the good stuff, the chemistry. To really understand any family of elements, you can't just look at the whole group. You've got to start small. We have to go right back to the beginning, to the fundamental building block, the atom. Now, I know the word atom can sound a little intimidating, maybe a bit abstract. So let's just forget the textbook definitions for a minute. Let's use an analogy. Just picture this. At the absolute core of everything, everything you can see and touch, is this one tiny, powerful thing, the atom. It's the starting point for, well, everything. You could say it's the main character in this whole story of chemistry. And right at the heart of our main character, the atom, you've got the nucleus. It's this dense core packed with protons and neutrons. To make this super easy to visualize, just think of the nucleus as the sun in our own little solar system. It's the heavy, powerful center of gravity that holds the whole show together. And what's orbiting our sun? Well, you've got electrons zipping around like little planets. Now, here's the secret sauce for chemists. While all the electrons are important, the one we really care about is the planet in the furthest outermost orbit. That single electron, man, it dictates almost everything about how that atom is going to act and react. That's the key. Don't forget that. Okay, so now that we've got a handle on the individual atom, let's meet the family. We're zooming in on a specific column in the periodic table, Group 1. And believe me, this group is a real family. They've got a super clear identity, and they all behave in very similar ways. And here they are. Say hello to Group 1, better known by their famous family name, the Alkali Metals. Now, the main players we're going to be talking about today, the real stars of the show, are the first three members, lithium, sodium, and potassium. Yep, so our main focus is on lithium, sodium, and potassium. But it's good to know that the family keeps going down the table with guys like rubidium, cesium, and francium. And just like any family, they all share these really distinct traits that tell you, hey, you belong to Group 1. And listen, these aren't just some abstract names in a textbook. They are literally all around us. Lithium, that's what's powering the phone in your pocket right now. Sodium, ever seen those bright kind of orange street lamps? That's sodium vapor. And potassium, it's a huge component in the fertilizers that help grow the food we eat. See? They're everywhere. So what are these shared family traits? Well, for starters, they're all pretty soft for metals. You could cut them with a knife. They have a low density, they're shiny, and they're great conductors of heat and electricity. All good stuff. But the most important point, the one thing that defines this entire family, is that last bullet point. They all have exactly one electron in their outer shell. Just one. That single detail, my friends, is their chemical DNA. It's everything. Okay, let's switch gears a bit. Time to put on our exam mode hats. Now, here's a super common mistake I see students make all the time. They just try to memorize a bunch of random facts. But that's not what the examiners are looking for. They want to see if you understand the trends, the patterns. So let's decode the patterns for Group 1. Here's the deal. There are two key trends for Group 1 that you absolutely have to nail down. First one's pretty straightforward. As you go down the group, from lithium to sodium to potassium, the atoms get bigger. Simple enough, right? Atomic size increases. But the second one, this is where it gets interesting. Their melting point actually decreases. Isn't that weird? They get bigger, but they become easier to melt. Let's look at the actual numbers. And hey, this isn't just some random theory. The data backs it up completely. Check this out.
Lithium up at the top melts at 186 degrees Celsius. Now take one step down to sodium, boom, it drops to 98 degrees. One more step down to potassium, and it's all the way down to 64 degrees. The pattern is crystal clear. You can't argue with it. So, the million-dollar question is, why? Why does this happen? Well, it all circles back to that one single, lonely outer electron we talked about. Think about it. As the atoms get bigger, that outer electron gets further and further away from the nucleus, our sun. The attraction gets weaker, kind of like a Wi-Fi signal when you walk too far from the router. This weak attraction means the metallic bond, that's the glue holding all the atoms together, is weaker. And if the glue is weaker, well, you don't need as much heat energy to break it apart. And that's exactly why the melting point drops. It's this beautiful, logical link between the atom's structure and how it behaves in the real world. All right, theory time is over. Let's put this knowledge to the test. We're going to walk through a real-deal SPM-style question. Because look, knowing the theory is great. That's half the battle. But applying it under pressure, that's how you win the war and get those marks. Okay, here we go. A classic exam question. First look, I know it might seem a little intimidating with that big S2O32- formula. But don't panic. Seriously, take a breath. The question gives us all the clues we need. All we know is some element M from group 1 is reacting with this thing called a thiosulfate ion. Our job is to figure out the formula of the compound they make together. Now, to crack this question, we have to focus on the most important concept we've learned today, the valence electron. Remember what that is? Just a quick recap. It's that one electron in the outermost shell. In chemistry, that little guy is the key to, well, pretty much everything. Okay, step 1, let's break it down. The question straight up tells us that M is in group 1. The moment you read that, a giant light bulb should go on in your head. Ding, group 1 means it has exactly one valence electron. That is the single most important clue in the whole problem. All right, step 2. Now we ask ourselves, what do atoms with just one lonely valence electron want to do more than anything else in the world? They want to get rid of it. They donate that electron so they can become stable. And when our element M gives away that one negative electron, what's left behind? A positive charge of +1. So it becomes the M+ ion. And now the final piece of the puzzle. We just have to balance the charges. The thiosulfate ion from the question is S2O3-2-. That little 2- tells us its charge. Our M ion, we just figured out, has a charge of 1+. So we have a -2 and a +1. To make them cancel out and form a neutral compound, we're going to need 2 of our M+ ions to balance the 1 - 2 ion, right? 2 + 1s balance 1 - 2. And that gives us our final answer, M2S2O3. And just like that, you've solved it. Excellent. You see, not so scary when you break it down logically. Okay, before we wrap up, let's do a super quick review of the absolute must-know, non-negotiable takeaways from all this. Think of this as your Group 1 cheat sheet. Okay, let's lock these in. Number 1, Group 1 elements are called the alkali metals. Got it? Number 2, their chemical signature is having just one valence electron, and they always want to donate it to form a +1 ion. Number 3, as you go down the group, their melting point goes down. Why? Because those metallic bonds get weaker. And number 4, for that very same reason, as you go down the group, their reactivity goes up. It's just easier to lose that outer electron when it's so far away from the nucleus. If you can remember those 4 points, you are in fantastic shape for the exam. So, I'll leave you with one final thought to chew on. You've completely mastered the trends for Group 1 now. You know they get more reactive as you go down because they're desperate to lose an electron. But what about the folks on the complete opposite side of the periodic table? Group 17, the halogens. Their entire goal in life is to gain an electron. So how do you think their trends for atomic size and reactivity are going to play out as you go down their group? That's your next challenge. Thanks for tuning in.